Today's webinar focuses on how to select the ideal X-ray detector for your specific application, emphasizing the various factors that influence this crucial decision. Not all X-ray detectors are created equal, and understanding the variables between them can significantly impact your investment. There's lots of different reasons why you might choose one detector over another, and some important factors that you should know when selecting your X-ray inspection system. By ensuring that the selected equipment aligns perfectly with your inspection needs, you can make a more informed and effective investment. Join us to explore the critical elements that will help you make the best decision for your application. In this webinar, we will provide a comprehensive overview of X-ray inspection, starting with the fundamentals of X-ray technology and its mechanisms for detection. We will explore the intricacies of various X-ray detectors, discussing their unique features and applications to help you understand which option best suits your needs. We will also take a deeper look at dual energy technology, highlighting its advantages and the critical role of image analysis in improving detection accuracy and reliability. Additionally, we'll cover other essential factors to consider when selecting an X-ray detector, ensuring that you make an informed decision that aligns with your operational requirements. We hope this session proves to be both informative and beneficial for your operations. X-rays are part of the electromagnetic spectrum of energy that includes radio waves, microwaves, infrared light, visible light, which is the only part of the spectrum we can see, ultraviolet light, which can cause sunburns, X-rays, and gamma rays. As the wavelengths in this spectrum get tighter, they gain the ability to penetrate various materials. This property is what makes X-rays particularly useful. They can pass through objects and provide valuable images based on a product's density. When X-rays pass through an object, denser materials absorb more of the radiation, casting a darker shadow on the detector. This contrast allows for detailed imaging of the internal structures of an object, making X-rays an essential tool in fields like healthcare and food manufacturing. X-rays occupy a critical position just beyond the visible light spectrum, enabling us to see what lies beneath the surface of objects without the need for invasive methods. An X-ray system is composed of three essential components that work together to produce and analyze images. The X-ray generator is responsible for creating the X-rays. It produces the radiation needed to penetrate the object being inspected. The detector, positioned opposite of the X-ray tube, collects the X-ray energy that passes through it. This component measures the intensity of the transmitted X-rays, allowing for the assessment of the material's density and composition. Then there is the imaging analysis software, the heart of every X-ray machine. This software processes the captured images and performs detailed analysis to extract meaningful results. Whether you are searching for contaminants, identifying quality defects in products, or conducting lean point analysis in meat, the software plays a critical role in quality control and process improvement. Ultimately, X-ray image analysis helps manufacturers enhance their operational efficiency by providing insights that lead to better decision-making regarding product quality and safety. Traditionally, food X-ray systems have utilized single-energy X-rays, employing a single beam of radiation at a specific energy spectrum to inspect products as they pass through the machine. These systems primarily aim to detect contaminants such as metal, glass, calcified bone or mineral deposits, stones, and high-density plastics or rubbers, particularly those injected with denser materials. As entry-level systems, single-energy X-ray machines are the most economical option available, featuring a line scan type of detector that has been prevalent in the food industry for approximately 25 years. While effective for basic contaminant detection, advancements in technology have paved the way for more sophisticated systems with enhanced detection capabilities. Yet traditional single-energy X-ray machines remain a popular choice among food manufacturers for their affordability and reliability in ensuring product safety and quality. When considering where to place an X-ray system in your process, it's important to evaluate the specific location to maximize its effectiveness. In the food industry, X-ray systems were initially positioned at the end of the production line, just before final packaging. This placement ensures that any contaminants are removed before products reach consumers, making it a critical and relatively straightforward installation area. On the other hand, placing X-ray systems in processing areas can be more challenging due to wet and harsh conditions. Furthermore, there's the option for conducting final case inspections, which also comes with its own set of unique challenges. Each of these locations presents specific hurdles that need to be carefully considered during the planning phase. For example, let's consider a hot dog manufacturer aiming to eliminate small bones from their product. Currently, the process involves running the product through a grinder equipped with a bone collection system, which is designed to remove a significant amount of bones. One option is to place the X-ray system at the front end of the production line. This allows for fat analysis to ensure the product has the right lean-to-fat ratio and helps remove larger bones before they enter the main production process. Another option is to install the X-ray system at the end of the line, where you've already invested money in packaging where it will remove the hot dog packages that still contain bone. Ultimately, it's a trade-off between where to position the inspection equipment and what you hope to achieve with that placement. Therefore, determining the right equipment location is crucial, as not all X-ray systems are the same and will offer different benefits depending on their placement. Let's analyze an example of a complex image featuring a large bag of pasta noodles captured using a single-energy X-ray system. In this grayscale image, you can observe various contaminants embedded within the product. To understand how single-energy X-ray technology works, it's helpful to compare it to a metal detector, which operates by inspecting products within a certain threshold. When using single-energy X-ray imaging, contaminants must possess a density higher than the threshold in the image to be detected by image analysis software. In this case, the X-ray image exhibits a significant amount of noise and busyness, meaning that only larger contaminants are likely to be identified. This is due to the fact that the density of the contaminants must be significantly greater than the standard deviation of the noise for them to stand out in the analysis. While single-energy X-ray systems provide a solid starting point for contaminant detection, they do have notable limitations, particularly when the product being inspected has a complex visual profile, as seen in this example of pasta. Organizations should carefully consider these limitations when selecting X-ray technology for their inspection processes. When it comes to X-ray detection performance, there are 3 key factors to consider when choosing the right setup. Speed refers to how fast your product moves along the production line. The faster the speed, the less time the X-ray system has to analyze each item. If products move too quickly, the X-ray may not capture a clear image, which increases the chance of missing contaminants. Higher speeds might also require stronger X-ray power, or could introduce more noise into the images. The materials your product is made of, known as product composition, greatly affect how well the X-ray inspection works. Different materials absorb X-rays differently, which impacts the system's ability to detect foreign objects. Knowing your product's makeup allows you to adjust the X-ray settings for the best detection results. X-ray energy levels involve 2 important components: kilovolts. This is the power of the X-ray. Higher kV means the X-ray can penetrate deeper into dense products to uncover hidden contaminants. Milliamperes measure the amount of usable energy that passes through the product for analysis. Higher mA means better quality data and more reliable detection. Any changes in these factors, speed, product composition, or energy levels, can significantly affect how well your X-ray system performs. By understanding and adjusting these elements carefully, you can optimize your inspection process to detect contaminants effectively and ensure product safety. When choosing the right X-ray detector for your products, several key factors are important to consider. 1. Chemical composition. The ingredients in your product affect the X-ray image. For example, products high in salt produce denser images because chloride absorbs X-rays well, resulting in darker areas. 2. Product thickness. Thicker products require stronger X-rays to penetrate and detect any contaminants inside effectively. 3. Packaging design. Packaging, especially if it has thick, hard edges like a large meat carton about 7.75 inches thick, can create dark areas that may hide smaller contaminants nearby. For example, a tiny metal piece next to a dark edge can be hard to spot. Similarly, a small bone next to 8 inches of meat may look very similar on the X-ray. 4. Production speed. The faster your product moves on the production line, the less time the X-ray detector has to capture a clear image, making it harder to spot issues accurately. 5. Image complexity. Products with busy images like a bag of pasta with mixed shapes and materials make it harder to see small contaminants. Smoother products like a block of butter are easier to analyze. Complex products may require advanced analysis tools or multiple energy spectrums. 6. Contaminant location. Where a contaminant is located matters a lot. Contaminants on the surface or in the center are easier to detect than those embedded inside or near the edges. Testing different product areas is essential to catch all potential contaminants. By considering these factors, you can select the best X-ray detector tailored to your product's needs and help ensure consumer safety. In this section, we will go in-depth further, exploring the crucial inspection variables impacting contaminant detection. Understanding these variables helps optimize X-ray system performance for reliable contaminant detection. Thicker products generally require more energy to penetrate in order to effectively identify contaminants. Utilizing a low-energy inspection source is often the optimal approach, as it minimizes the energy requirements for the inspection process. This not only enhances the efficiency of contaminant detection, but also prolongs the lifespan of the inspection equipment, particularly the X-ray tube, since it operates under less strain with lower energy levels. Typically, the main factor influencing the lifespan of your X-ray tube is the milliampere setting. Generally, the lower the mA, the longer the X-ray tube will last. However, if your product is particularly thick or has a high salt content, such as cheese, you may need to increase the X-ray energy to achieve effective penetration. In the provided X-ray images, both a loaf of bread and a block of cheese display contaminants. The cheese, which contains significant amounts of chloride, presents a darker image due to the increased radiographic density created by the salt. This phenomenon occurs because the chloride enhances the X-ray absorption, creating a darker image, even though the product is smooth. The less dense bread allows X-rays to pass through more easily. This results in a lighter image overall, with the contaminants appearing much darker against the background. This illustrates how variations in product density and thickness can significantly impact detection technology and the power requirements needed for effective inspection. As we mentioned earlier, understanding product composition is crucial when selecting X-ray technology. Uniform products like peanut butter, while smooth, pose unique challenges related to their packaging. Features such as the jar crown, the bottom, and the crevices along the top can obscure contaminants and require specialized detection strategies. X-ray technology offers zonal inspection capabilities, allowing for targeted examination of specific areas while omitting others. This is particularly advantageous for inspecting intricate packaging designs where contaminants may hide. Thus, the choice of detection technology should be influenced by the product's packaging as well as composition, whether it is homogeneous or textured, as it significantly impacts the effectiveness of the inspection process. When inspecting non-homogeneous products like cereal or pasta, the imaging can become quite complex due to the varied composition of the product itself. This complex imaging scenario is due to the high number of intersecting angles, leading to busy images that may complicate detection. In such cases, contaminants must possess a higher density or a greater standard deviation compared to the surrounding material to be effectively detected. Therefore, the focus shifts to identifying density changes within the product. Cereal is classified as a grain product, which typically exhibits low absorption values. This characteristic can complicate detection efforts, making it challenging to differentiate between the product and potential contaminants. To enhance detection capabilities, employing dual-energy X-ray technology is recommended. This advanced method allows for improved differentiation based on density variations, thus increasing the likelihood of identifying unwanted contaminants within the cereal. Packaging type significantly influences the effectiveness of product inspection. As previously mentioned, some packaging types present greater challenges for detection than others. For example, consider a can with a pull tab. In this scenario, contaminants could be located anywhere inside the can, including under the tab. To successfully detect a contaminant, a certain level of contrast is necessary, especially near the edges or bottom, depending on the can's orientation. Typically, this type of product would be inspected using an X-ray system equipped with side view technology. However, if the cans are positioned in a case on a traditional overhead belt system, the inspection would be conducted from a downward angle, as illustrated in the example. Therefore, understanding the packaging type is crucial for optimizing inspection strategies and ensuring effective contaminant detection. Production speed plays a critical role when choosing an X-ray detector. As products move faster along the production line, the integration time for the detector decreases. This shortened analysis time impacts the choice of X-ray technology used. For high-speed applications, such as metal cans and flow-wrap products like energy bars, single-energy X-ray systems are often the most suitable option. These systems perform exceptionally well at high speeds, typically ranging from 150 to 400 feet per minute, where speed is prioritized over the power-to-cost ratio. In these scenarios, the focus is on achieving fast, reliable inspections without the additional costs associated with more complex systems. Linear array detectors are particularly advantageous in these high-speed environments, allowing for cost-effective solutions while maintaining efficient performance. Dual-energy X-ray technology is more effective for products from natural sources like bag salads, where contaminants are naturally occurring non-organic and imaging is complex due to low density and water content. Dual energy distinguishes between the product and contaminants such as stones, field glass, or metal. In the meat industry, dual energy is essential for detecting bones amid complex images. This technology also benefits the inspection of slower-moving raw materials like nuts, 80 to 200 feet per minute, which allows detailed and accurate contaminant detection without compromising inspection quality. Ultimately, while high-speed systems can increase production efficiency, careful consideration of the type of X-ray technology used is essential to balance speed, cost, and detection accuracy, and must be tailored to the specific needs of the product being inspected. Here are additional examples of smooth X-ray images. When the image quality is high and smooth, objects tend to stand out prominently. However, the location of contaminants becomes a crucial factor in detection effectiveness. Even if a product is less dense than a contaminant, the placement of that contaminant can complicate detection efforts. For instance, in the far right image, there is a contaminant located at the very edge. This represents a challenging detection scenario because it blends in with the uniform gray background on the left. Detecting contaminants in such positions can be quite difficult. When inspecting X-ray results, it's essential to position potential contaminants in various worst-case scenarios throughout the package. This approach ensures that your detection system is reliable and capable of rejecting any contaminated products during production, regardless of where the contaminant is situated. This brings us to detector technologies in the food industry. There are three main types: linear array, time-delayed integration, and photon counting technology. We will go into more detail of these three technologies in the following slides. Detectors should possess a very large dynamic range to capture the full spectrum of energy penetrating the product. This capability ensures that whether a product is exceptionally thick or extremely thin, the detector will not become saturated or underexposed, thereby maintaining image quality under all conditions. In addition to dynamic range, pixel size plays a crucial role, much like TV resolution levels such as 720p, 1080p, 2K, or Ultra 4K. A finer resolution leads to a crisper and clearer image. However, smaller pixels absorb fewer photons, which can increase noise if not balanced with sufficient energy. With a smaller pixel size, you achieve extremely high resolution and exceptional image detail. This often requires more energy or slower product movement to ensure adequate photon capture. Otherwise, the image quality might suffer due to increased noise. Thus, the choice of resolution and technology should always be guided by the specific application requirements, ensuring that the chosen setup meets the desired specification without unnecessarily compromising on image quality or operational efficiency. Approximately 98% of the detectors available on the market today employ a scintillator, which is a type of ceramic material that absorbs X-rays and emits light as a result. Beneath the scintillator, a photodiode converts this emitted light into an electrical signal, which is then processed by an analog-to-digital converter to create an image. A linear array consists of a single row of photodiodes topped with a scintillator. As a product moves in a straight line over this array, it generates an image in a manner similar to an old fax machine. The scintillator converts incoming radiation into visible light, which is captured by the photodiodes, effectively recording a single line of data at a time. This line of information acts as a shift register, progressively building an X-ray image line by line as the product passes through the beam. Each line captured contributes to the overall image, allowing for detailed imaging of the product by capturing variations in density and composition along its length. As the product continues to move, additional lines are acquired and stacked sequentially, gradually forming a complete image. A TDI detector is a type of line scan where multiple diodes are arranged in a row. As the product moves over the detector, the outputs from these diodes are stacked to form an image with improved resolution. Each subsequent row adds to the previous one, effectively increasing the exposure time without slowing down or stopping the product's movement. This method results in a lower signal-to-noise ratio, higher resolution, and the ability to use lower energy levels to achieve the same image quality as a traditional linear array. A line scan detector using TDI technology is an indirect detection system that comprises a scintillator and a photodiode arranged in a linear array. In this design, the detector features multiple photodiodes in a row, sometimes just two, but often many more. Increasing the number of diodes enhances the resolution by capturing additional data points across the scanned image. This allows the system to produce high-quality images by effectively gathering optical signals as the object moves across the detector. With TDI detectors, calibration is critical, especially when considering the product's speed and thickness. Unlike linear array detectors, which are simpler, lower cost, and easier to integrate, TDI systems require a more precise setup. In TDI detectors, a product is scanned multiple times as it moves across the detector, allowing the outputs from the multiple diode rows to be stacked and merged. This stacking enhances the image resolution and reduces noise by extending the effective exposure time without reducing the product's motion. However, when calibrating a TDI system, careful attention must be given to the product's height. For products with significant vertical dimensions, the calibration should target the center of the product. This is vital because a contaminant at the top of the product may move at a slightly different speed than the bottom. If the calibration is off-center, the resulting image may suffer from blur or distortion. For example, contaminants present on different parts of a tall product would be misaligned, causing the defective area to appear elongated or less intense than intended. By calibrating to the center, any discrepancies in motion are minimized, ensuring that the image is accurately constructed and that features such as contaminants are clearly defined. While TDI detectors provide superior imaging performance with higher resolution and lower dose requirements, they demand precise calibration, particularly in terms of synchronization with the product's motion and height, to avoid misalignment and ensure image quality. The latest advancement in imaging technology is photon counting, which represents a significant departure from traditional systems. Unlike older setups that rely on scintillators and photodiodes, photon counting technology converts X-rays directly into electrical signals. This direct conversion leads to faster processing speeds and eliminates issues related to afterglow in images. In conventional systems, scintillator materials emit light when exposed to X-rays, and this light diminishes slowly after the X-ray source is removed. This lingering glow can cause blurring in the resulting images. However, photon counting technology avoids this problem, producing exceptionally crisp images without the need for physical filters to differentiate energy spectra. While photon counting technology offers superior resolution and clarity, it does come with challenges. The system is more complex and has a higher cost compared to traditional imaging technologies. Nevertheless, the outstanding image quality it provides makes it a compelling option for high-precision applications. Later, we will explore the physical filters necessary for traditional dual-energy systems, highlighting further contrast with photon counting technology. In this section, we will talk more about dual-energy detectors and the additional value they offer. Now, let's delve into the filtering effects of dual-energy X-ray detectors. In traditional dual-energy systems, the setup involves two distinct photodiodes or detector sets, a low-energy detector and a high-energy detector. To effectively filter out low-energy photons, a material filter, commonly made of copper or similar substance, is employed. This filter blocks low-energy X-rays, ensuring that only higher-energy photons reach the high-energy detector. The design necessitates a curved detector arrangement to allow both low and high-energy X-rays to interact with the same photodiode as they traverse the beam path. In the detector setup, you will observe that X-rays emanate in a cone shape. It is crucial for the detectors to be aligned such that they capture the same photons consistently, which is achieved by the curved configuration. The complexity of this system arises from the need for precision in stacking the detectors to ensure that both energy spectra are processed through the same diode. The physical filter plays a vital role by absorbing low-energy photons before they can reach the high-energy detector. Consequently, this setup allows for the determination of a material's atomic composition by analyzing the ratio of detected high-energy to low-energy photons. To define the energy ranges clearly, one might set the low-energy threshold at 0 to 70 kV and the high-energy range at 70 to 140 kV. By taking this ratio, we can make informed conclusions about the material under examination. This filtering mechanism not only enhances the accuracy of the measurements, but also facilitates a more effective analysis of the material's properties. Dual-energy detectors represent a significant advancement over traditional line-scan X-ray systems, which operate using a single energy beam. The dual-energy approach employs two different energy spectrums, enabling the system to discriminate between high and low channel X-rays. This differentiation allows for a secondary energy beam to penetrate denser products, thereby improving the detection and visibility of foreign contaminants. Eagle's proprietary technology, known as Material Discrimination X-ray, or MDX for short, exemplifies this approach. In parallel, you also encounter the term DEXA, a medical acronym for dual-energy X-ray absorptiometry, which is used to analyze various material types based on their atomic composition. Additionally, the system referred to as PXT integrates dual-energy technology with time delay integration and multispectral data, further enhancing image analysis and material discrimination. MDX is Eagle's traditional dual-energy solution. The outcome of this detection process is the differentiation between organic and inorganic materials at specific energy levels. For instance, consider an image of a bag of chocolates. This image presents a complex challenge for a single energy X-ray due to the numerous components involved. However, when analyzed with a dual-energy detection system like MDX, glass contaminants are easily identified. At their core, all X-ray companies function as image analysis companies. Hence, superior image analysis directly translates to improved detection capabilities. This highlights a significant advantage of dual-energy detection over traditional single-energy detection methods, as it enhances the accuracy and reliability of identifying various materials within a sample. DEXA uses dual energy in fat analysis systems to discriminate between material types. This is specific to meat products to determine the fat, lean, and moisture content of the raw product. We take the high and low energy ratio information and apply algorithms programmed in the software to measure lean versus fat, and then the residual is going to be your moisture. One of the primary advantages of DEXA is ensuring that products are purchased at the optimal price while maintaining the correct blending ratios. This technology helps reduce inconsistencies in operations and enables the identification of preferred suppliers. For instance, consider a hamburger producer with a specific recipe that requires an 80-20 ratio of lean meat to fat for their patties. If the producer sources from 10 different suppliers, they might receive product variations with lean percentages ranging from 90% to 50%. By installing an X-ray system at the receiving end of the facility, the producer can easily analyze the incoming product stream. This real-time analysis reveals that supplier A consistently delivers lean meat at 90%, which is the higher-priced option. Meanwhile, another supplier offers meat with a lean percentage of 95%, which is also higher than desired. With this information, the producer gains valuable insights into their supplier's products and can make more informed purchasing decisions. This capability not only helps in optimizing the blend in their hamburger patties, but also ensures they are maximizing the value from their suppliers by adjusting their sourcing strategy accordingly. Ultimately, this leads to better cost management and product quality in their operations. Moreover, a meat processor might discover that another supplier consistently delivers products that meet specifications perfectly. However, there may also be suppliers whose products contain higher levels of contaminants. By utilizing DEXA technology, contaminants can be identified, which can provide valuable feedback to those suppliers so that they can improve their processes. Ultimately, the goal of a fat analysis system is to enhance efficiency throughout an operation. This involves scrutinizing the entire value chain to ensure that suppliers are delivering the quality products are paid for. If there are opportunities to take advantage of favorable pricing, a meat processor or slaughterhouse wants to ensure they are making the most of those benefits, whether it's receiving premium quality at a lower cost or addressing any issues with contamination effectively. Next, let's explore our latest innovation in dual energy detection, the PXT, or photon counting X-ray technology. In the images displayed, you can observe a clear distinction between the two systems. On the left, the standard dual energy MDX image appears somewhat grainy, which can hinder the detection of finer details. In contrast, the image on the right, produced by our enhanced dual energy technology, is significantly clearer and smoother. This improvement not only enhances image quality, but also makes it much easier to identify smaller contaminants, elevating the overall effectiveness of our detection capabilities. Inspecting chicken breasts presents unique challenges due to the presence of calcified bones and varying tissue densities. Traditional X-ray systems require high power levels to achieve the necessary image clarity for detecting contaminants and bones, which often leads to quick burnout of the X-ray tubes, making the inspection process costly and inefficient. However, with the introduction of PXT photon counting X-ray technology, it's possible to utilize lower power while still obtaining remarkably clear and detailed images. This advanced technology allows for the detection of low-density bones, such as fan and rib bones, which are typically difficult to identify in conventional inspections. As a result, processors benefit from a reduced total cost of ownership while maintaining high standards for contaminant detection. By effectively filtering out the surrounding meat, this technology enables the identification of small bone fragments in those hard-to-reach areas, thereby enhancing product safety and quality. Historically, locating contaminants in fish fillets, such as bones, has posed significant challenges. In the standard X-ray image displayed at the top, detection capabilities may be limited. However, the bottom PXT image of the same fish fillet reveals a clearer perspective. Here, one prominent bone is clearly visible in the center, while the smaller pin bones are also distinctly identified thanks to enhanced resolution. The image analysis software excels at distinguishing between objects that should not be present and the edible components that are supposed to be there, leading to improved quality control in fish processing. Detectors and machine design are key to X-ray inspection systems, but the real difference comes from imaging software. While capturing images is important, how well the software analyzes them determines the machine's value. Advanced imaging software boosts defect detection, simplifies quality checks, and improves efficiency, helping ensure top product quality. Consider a basic X-ray system designed to reject contaminants, such as a piece of metal on your production line, or to ensure accurate counts in packaging. One example is if you're assembling an 8-pack of hot dogs and one package contains only 7.5 hot dogs. It's crucial to detect and reject that defective item before it reaches customers. However, imaging software can do much more than just basic rejection. By analyzing the data captured during X-ray inspections, you can identify trends and patterns in your production line, paving the way for meaningful improvements. This data can reveal when defects occur, allowing you to pinpoint potential entry points for contaminants or errors. Using this information strategically can be invaluable in investigating these issues and implementing corrective measures. By effectively utilizing X-ray imaging analysis, you can transform it into a powerful tool that enhances product quality and operational performance. Simultask Pro, Eagle's proprietary image analysis software, is recognized as one of the most advanced solutions on the market today. It is a customizable software that can be tailored to your specific product applications. With the highest grayscale range of up to 65,535 values, its advanced image processing algorithms provide high-resolution images with deeper contrast and extraordinary details. Additionally, it excels in performing simultaneous inspection controls during a single pass, even at high line speeds. Consider a scenario where the line processes both bone-in and boneless meat items. Simultask Pro allows for customized inspection methods tailored to each product type, enabling the collection of separate statistical data for comprehensive analysis. Furthermore, all information is stored centrally for easy access, facilitating informed decision-making to enhance the efficiency and effectiveness of your production line. By leveraging Simultask Pro, you can ensure that your inspections are not only effective, but also adaptable to the diverse needs of your product range without a lot of human intervention. When choosing the right machine configuration and detector types for your X-ray systems, several key factors must be considered. There are various detector sizes available, such as 0.4 mm, 0.8, 1.2, etc., but selecting the one with the smallest number isn't always the best choice. Instead, focus on the detector that best meets the objectives of your food safety program. Evaluate your production line, application specifications like speed and contaminant detection needs, production environment, and budget to determine the optimal solution for your operation. It's important to understand that not all X-ray machines are the same. A critical differentiator is often the image analysis software. X-ray systems aren't a one-size-fits-all. The best system depends on the specific outcomes you want to achieve. For instance, if your goal is to satisfy a basic customer audit or perform simple contaminant detection, a basic X-ray machine might suffice. However, always assess your unique production needs and budget before deciding. Choosing the right X-ray vendor is equally vital. Ensure they understand your specific requirements and can offer a customized solution. Product specifications should align with your budget, expected return on investment, ROI, and contaminant detection needs. Since all X-ray equipment may experience downtime at times, select a vendor you can trust to provide prompt and reliable support when issues arise. At Eagle Product Inspection, we stand behind our products and strive to be a trusted advisor. We have a strong escalation process and the expertise to help you define your application needs and ensure quick recovery from any issues. When you partner with Eagle PI, you gain a committed ally dedicated to helping you maintain optimal production line performance every step of the way. We've talked separately about detector options, dual energy, and how X-ray companies are essentially imaging companies. Having the ultimate combination of these technologies will add tremendous benefits to your line. Eagle's PXT dual energy photon counting technology, paired with Simultask Pro image analysis software, forms the ultimate dynamic duo in product inspection. When combined, these advanced X-ray technologies capture higher resolution images and perform real-time analysis within 1/10 of a second, setting a new standard in bone and contaminant detection. The perfect partnership for total product safety. Discover why the dynamic duo of PXT and Simultask Pro is the industry's top contaminant detection solution. Download the ebook today by visiting eaglepi.com/dynamicduo to learn more.